We discussed the transform domain previously, which was the domain. Although we already covered the very basics of everything in the image processing. So if you are actually, you have a very good background now to basically build on the problem. But however, there are some other transformations which are also important, which are better than Fourier transform. So in this set of slides, I will give you just overview that what are the transformations in general and how you can apply other transformation on an image. So it will give you an idea. And definitely, if we start working on wavelets or other domain, what will happen is it will take like a whole course. What I will give you, I'll give you a background. So you can build on the top of that. It will be for you to start and working on the wavelet. And this again, I will make the basis as a Fourier transform. And based on that Fourier transform, I will start building on it. So here I will discuss why Fourier transform has some issues. And then we can go to which we call it the short-time Fourier transform. Then we discuss the discrete cosine transform and Wavelet transform. But however, most commonly found are discrete cosine transform and Wavelet transform. Why we use it, we'll discuss in this class. So in general, what is a transform? Because here in this slide, we discuss about different types of transformation. So I have to generalize what do we mean by transformation. So transform is a mathematical operation that takes a function or a sequence and maps it into another sequence. Yes, this was what we did in Fourier, right? So why transform are good? Because it may give additional information in terms of frequency that we have. So also, sometimes the transformation into another domain is much easier to handle in terms of mathematics. Also, sometimes transform requires less storage. And what is the advantage of that? Like for example, what is the example of that? Why like transform may require less storage? For example, simple example. Give me a simple example. So let's say I have a sign. Instead of storing all the samples, I just store one sample delta function of specific frequency and I can generate it back. Similarly, applying operation can be easy in transform domain, and we have seen this in terms of high pass low pass. It was easier. So now let's say we have different type of sinusoidal waves. So what is the difference in terms of frequency? Definitely it has less, it has more frequency, and it has the highest frequency. So if I see all these transformations, these signals into frequency domain, I can see these type of pulses, right? It's very easy example, no problem about that. But however, now even if it's a mixed signal, we have this is the combination of three previously, right? So here, if I want to store this, it is a very difficult to store and analyze as well. But here, if I see that it has three components, very easy to see. If I want to filter one of them, I can just kill one of them and that's it, right? So there's a lot of advantage of it. But all this thing, what we assume is that from 0 to 1 second or for whole the time, the waveform is same. It's not changing. The behavior is not changing. But what if it's changing? We call it what we call it if the waveform changes with time. So what this is the case of stationary. But so what if it is not stationary? So what will happen? So what we can do, we need a technique that can march along the time and give me at each instant what is the frequency. And we will also see that, let's say I apply Fourier transform on the non-stationary signal. What's the problem? So analyzing spectral quantity in different places, this will help us analyzing the spectral quantity in different places and also detecting the sharp changes in spectral characters. So these are the characteristics if we do this. Now again, fine, I know that this is stationary, but let's say I apply the Fourier transform on non-stationary signal. So what's the problem? Now this is a stationary signal. I get very nice 3 pulses. And this is a non-stationary. You see this frequency is high and then becoming low. So Fourier transform again gives these frequencies. However, if I want to inverse transform, I will not get this thing because this assumes that signal has these frequency for whole time. So it will be that if I do inverse transformation, that will give me some of these frequencies in time. So it will not be this thing because the timing information in other words is lost. Yes or no? Yes. Good. And we can see easily from this one. Let's say you have this type of non-stationary signal, you have low frequency and high, and here you have high frequency and low. So if I use a Fourier transform, because timing information has been lost, assuming the Fourier, in other words, the Fourier transform assumes that signal is same for whole frequency. And similarly here, where we have the image, and this is like just an example that we have sinusoidal signals, but it's changing with the axis. It's not stationary. And this is what image is, right? Because in images, you have details that are changing. Fourier transform only gives frequency component in the signal, the whole signal. The time and frequency information cannot be seen at the same time using the Fourier transform. And the solution is time frequency representation. So in other words, that the Fourier transform is stretched into infinity in time, no time localization. No time localization, which frequency is present at which time. So what I'm talking about is the Fourier transform. Yeah, I'm coming to that one, but I'm talking about the Fourier transform. When I take the Fourier transform, I lost that time information. Which frequency is present at which time, I cannot tell. So that's why what we need to do is, it's good in spectral localization, like sinusoidal gives the one pulse, but in time localization, no, it's not good. So this type of analysis, which we call it the global analysis, does not allow analysis of the non-stationary signals. Non-stationary signals are signals which are changing with time. So what we have to do is we have to do bundled Fourier transform. Instead of taking the whole signal and trying to find the Fourier transform, I just take the chunks of that. So in this way, I will retain the information of the time and the frequency.
Time localization doesn't phase play.
No, it's the structure. The timing is time. Which time is this frequency is present?
If I have reference, I have phase that reference and frequency. What times?
Phase tell you the let's say you have two sinusoidal, same frequency but different phase. In other words, let's say this signal. If it's starting from here, I have this thing. But if I start here or here, the phase changes. So this information is reflected in phase. But which frequency is present at which time? Still, I am not. You see what I'm saying? Okay, so phase information is not giving you the timing, exact timing. Yeah, it's giving you where it's starting and delaying, but not the exact.
Just even I can have starting with high frequency, it will be shown at the end of the spectrum, and then at the end, I'm getting like small bands of frequency. So it will be shown. It just has nothing to do with time. Okay, I just
You see here, low frequency, high frequency, right? Here what we have, high frequency, low frequency. But if I plot the spectrum, I get the same thing. Why? Because it does not have the timing. So now what we have to do is we have to go towards it. We take the chunk, and the chunk or the window is such that at that window, the signal is assumed to be a constant frequency. So I have this, the window is like a hyperparameter, the length of the window, and the shape of the window as well. Use a window of a special kind, let's say Gaussian window. We'll discuss this. Anyhow, this is short-time Fourier transform. We take a small chunk. So how we do? Choose a window function of finite length. You have to take the length of beside the length of the window and the shape of the window, and then place the window on the top of the signal at t equal to 0. Truncate the signal using this window. So that part which are inside the window should be taken. So let's say I have any signal and it's changing with time. So I will just take a window here. So once I taking into this window, I'm assuming that other are actually not there. That part, and taking the STFT of that. STFT or Fourier transform of that, and then again the other window, and it depends. It can have an overlap or it cannot have the overlap. No.
if you continue, show her how it will look like. I think she will understand. This
Yeah, I'll just wait for it. I have this slide that. So I have to compute STFT and then move and repeat that for each part of the signal. And this is compute FT of the truncated signal, save and increment the side of incrementally slide the window to the right and go to step 3. You have to repeat until reached at the end of the sample. I will have an examples and it will clear. So mathematically, what I'm doing is I'm doing the Fourier transform, but I'm not doing the Fourier transform on the whole signal. So what I'm doing, I'm just multiplying that with something that will take that part, and then after that I take the Fourier transform. Simple, right? So it is continuous and this is discrete. Nothing special here. And this is some example. So what I have to do, I have to have first section window length of this, and then I take the I take the Fourier transform, and then I move another part. Now how much I move? This is called the hop size, and it is depend on how much processing I want. If I have a good processor and signal is not very huge, this is like to give you the high resolution if I just hop by one sample. But I can skip some of them. Even I can have a non-overlapping windows as well. But that will definitely lose some resolution. Will lose some details. Record hop size, or also we discussed in the MATLAB, we have how much percentage overlap I want between the two windows. So here you see, if I take a window here, I know that here the frequency is almost one type of frequency, and then if I just go to another part, here the frequency is different. So if I take the Fourier transform and plot it, it will give me the frequency information at each instant, right? Again, this different window, then different windows. Now, how to arrange it? I will just go to another slide as well.
I think 50% overlapping.
It depends. Definitely, like one hop of one size will give you the best results. But again, it depends on the application. But again, here what I'm doing, I'm just taking this part, which we call it window. But some of the people then they come up with another idea that I'm just taking this window. Through what I'm doing, I'm multiplying this portion with 1 and other with 0. This is what I'm doing mathematically. So I'm just like doing multiplying this and then taking the FFT, then multiplying this thing and then taking the FFT. So basically, I'm multiplying it. I'll call it rectangular window. Now, if we have a rectangular window, why not to have Gaussian window? Fine. And what's the good thing about the Gaussian window is because Gaussian has a smooth edges here. So if I plot it, it will give me a very smooth Fourier transform as compared to, because of sharp transition, I'll get the high frequency components. And definitely you can propose your own windows. There's a lot of windows, even there are a lot of research on which type of window should be used. Fine. So again, I just slide and just try to find each step. But the question is, if I slide, what should I do? So many transforms, right? So I have to find a way to visualize it, right? So what I do, I take a window, and after taking that window, let's say this one, whatever come inside, like after taking the FFT or DFT, I just arrange it in this fashion. The same thing in this one, and then another. So I have a timing information here and the frequency information here. Make sense?
Now I'm taking this one, doing DFT, then IDFT. What's the difference to make a window or Gaussian?
The Gaussian will give you smooth edges here. Otherwise, if I just use a rectangular, I will see the high frequency here, high frequency components here.
But I'm using it just like maybe to convert like 1D to 2D, then at the end have a turn back.
Yes.
So does it make the window shape will make a difference?
Will make a difference if you want to process this thing, because there will be some high frequency component which is not from the image but from the window. So if I want to process, let's say, applying some filter or maybe some CNN or whatever, these high frequency components will play some role. Gaussian will not have it. Fine. So how it works in like Python or MATLAB, let's say I have this signal and I have a window of size 2. So I will just take these two, take the FFT, put it here, and this is overlap, and then this one, and so on and so forth.
50% overlap.
Here 50% is because of 2. And we have some script if you want to do that. Is this clear your question?
I still think my answer is something. Because so whatever window size I take, that means within that window it cannot differentiate between times.
Yes, inside windows there's no time.
So I am sampling without quite of time as if it's only a moment of time because I lost that information. So that's why it sounds like sampling.
Sampling in which domain? Not time, but I can say in frequency if you want to have, or it's sampling. Yes.
We're assuming whatever the FT is, we're assuming all of that happens at the same time.
Yes.
So
in other words, you're saying that the sampling is there. This is what you wanted to say. More sampling will make it more good.
So the bigger the window, that means I'm losing more.
Yes.
I'm sampling data. Because the smaller the window, the more I'm representing what my signal actually is.
Yeah, but fine, this makes sense. But what's the relationship in between sampling and this window?
It's the same thing. I have a squiggly signal, and I need to sample the signal. I can sample it with a very small.
Because the signal is already sampled. This is sampled signal. All the signals that I'm talking about is sampled already. This is sampled signal.
This is some in
Yeah, because we already did in first lecture the sampling. So now we are not discussing any continuous. This sample thing, but plotting it a continuous way, like in a MATLAB, let's say plot. Yes. So it's already sample. Yes.
Yes.
I hope it is.
But the way I see it, we are just converting 1D to 2.
Yes. This is. But why? The question is why. So just trying to understand this thing that why I want to convert one.
No, because-
And for non-stationary, definitely one is not stationary. The other is also that. Let's say your signal is stationary, but I want to include both information. Let's say I want to use it for the CNN or something. So I use both information of time and frequency and give it to network. Maybe you can learn better.
But if now you're compensating, you are taking 2D and you want to make it 3D. So we are like wavelets.
We talk about it. So now here what I'm doing, and now the same thing. If I apply image, I can take this thing here, 8 pixel by 8 pixel window, and then move either overlapping and this, and now it will become 3D. I can arrange in a 3D fashion. Similarly, here I change the size by 32 pixel by 16, and then here it is 32 by 32. So making you can have your own choice of window size. So I think
We change the window every time we change, or we
have to keep it same.
Because here it's just changing.
It's different examples. Yeah, I can have this or this.
The first 2 columns.
Yeah, at the end you have to put some zeros here.
Zeros.
Yes, so that's why it's because to cover it. Again, so I think it's the same thing that we discussed. STFT gives you time frequency information, and the main thing for us is that I can transform 1D to 2D and then apply the signal processing concepts. And this is what I told you even from the beginning, that even if you are interested in working 1D transform 2D, you will have larger domain. Similarly, the shape of the window can be anything: Gaussian, rectangular, elliptic. Wider the window, we have poor resolution, as you also mentioned. Narrower the window, we can have the good resolution. However, definitely we'll have more samples, the more data. Yes.
Why window will give you less resolution? You are capturing everything in that window, regardless. It's small.
No, it's like, for example, again, if you are confused, try to understand that what is a sweep signal. So wider the window, what will happen is that you will have two frequencies. You will not have exact location. But again, smaller may not capture the whole wave, right, or whole frequency. So you have to do some analysis or some hit and try, or maybe analyze your signal that where I can have what can be the size of the.
Because later on, like we have a 1D signal and then convert it to 2D. What I'm getting all the time and the frequency I'm getting really is just how to stuff. You get everything. So I'm capturing everything, guys. So
you are capturing everything, but the time information will not be correct. If you have a more wider window, then it's like behave like a simple Fourier transform, because there are two frequencies, let's say 1 and 2, but that two frequencies are not separate in time. So still, in other words, the resolution in time and frequency will not be good. Fine. Now see, what up till now we did STFT, right? So in STFT, what I'm doing, I have the signal here, and that signal should not like this. So and that signal, I just break down using window, yes, like this one and this one. So basically, I take the signal whole, but I'm breaking down. But if now see the difference between the wavelet and this. When we are doing the wavelet, we are doing the opposite. We take the whole signal, but inside this window is what? It's a sine waves, right? Sine waves, different sine waves, because I'm taking the Fourier transform. So I'm in the window, I'm distributing among the sine waves. So this is what, if you think about it, it will be like wavelet, because this thing for this is only exist here. After that, it's not existing. And what is wavelet?
Wavelength or what?
Wavelets. What is wavelets? Wavelets, and wavelets is what? Small signal for short duration. A signal that is for short duration. Okay, so basically, STFT is basically a kind of a wave. Why? Because I am just taking a small signal here for this purpose, small signal here and small signal here. But however, why did not call it wavelet? Because normally the wavelet is something die down, like this one, or maybe like this thing. So it should die down in order to call it a wavelet. So the wavelet is, what's the difference between the Fourier transform and wavelet? Fourier transform, you have a sine wave and do the same process by spreading the signal into the sinusoids. Wavelet, instead of sine, we have wavelet, and I spread all the signal into this, and which make much more sense, because not necessarily all the signals should be baked down into the sinusoids. Cannot be, right? Because I'm assuming that this signal is a sum of sinusoids. It is like a very wide, I'll say, very worse assumption, but not necessary. It can be. It is more suitable to have short waves, and even in images, we have edges. So as images, if I break down into wavelet domain, it will make more sense to have sinusoid, because I cannot assume the signal that has so many information I can break down into sinusoid, which cannot be, right? Although I can, but it's not. Now, before moving to wavelet and other transformations, I want to generalize our transformation that we did previously. Previously, what transformation we did? DFT, right? So DFT, what we had? This type of expression, right? Yes or no? Have you seen that one? What is R here? T power 2 pi xu over n here, and similarly inverses. Yeah. So fine. Sometimes also we write here 1 over n, or in some of the books and even in this chapter as well. Instead of this, this term is multiplying with 1 over under root n, and this is again multiplying with 1 over under root n, just to make sure that both are multiplying with the same. So don't confuse yourself. You can use any of this. I have no problem. So don't confuse yourself if you see this or this. But generally, you see, because this was Fourier transform with exponential, but I generalize it with this term, which is a function of x and u. So I can take here anything instead of exponential, and this will give me another transform. Yes or no? So what it means, if I take anything here r, what is logical? What I mean, I am basically that I am decomposing my signal into that and yes. So let's say now for Fourier, I have sinusoidal, right? But let's say take a square wave. So what I'm doing is I am dividing or distributing f of x, my signal, into these squares. I can have these sawtooth wave, or I can have again wavelet. simple, just wavelet. Wavelet is what? Simple signal. It is wavelet. So now if you understand this, you understand everything. Now any transformation is basically, but definitely I cannot have anything in this R, but it should have some property to satisfy. Yes or no? Good.
Maybe write the paper of R x y equals 1 to the power 0.
Now I will just show you. You see, now if I can open this thing, this part, if I just open it, so I can write in this fashion, right? If you remember, it was W before. Before it was W, right? So it is like this, right? And I wrote it like this, WF. Remember that? But here I'm generalizing it. Why I'm generalizing it? Because if I generalize it, I can have any transformation I want.
Transform the is in 3D, right? Only 2D.
1D will be 2D and 2D will be 3D.
Then I will convert to 1D signal converted by STFT to signal, then converted by wavelet to.
Then we can. But it depends on how what you want. Huh? So now you have this thing, right? Now defining this matrix will give you a transformation. Fine. So we'll go a bit detailed. So in general, I can write, and this was again only the notation is changed because previously I was just discussing Fourier transform. Here I'm just discussing in general. So therefore, this is a signal, but type with A matrix, which is this A matrix, and this is F. So previously call it W, now it's like A, and this is F. And now one of the property of A is that A inverse equals to A. This is a good thing because you don't need to inverse it. And if you want to have your own transform, you have to make sure about this. Otherwise, it will not be. You cannot reverse it or inverse.
But if now if A is like n by n or n by n, then A trans they will be same.
Still you can get it because if it means this A transpose equal to what?
1
Identity.
But if we have A by n size, then this
A is what? A is what?
3 by 2.
3 by 2. Huh? And what it will be? 2 by 3. So what it will be? 3 by 3. Yeah, so the inverse, but I think because it's not needed. Inverse is equal to A.
This is only the true because I don't know the true.
A transpose. But again, the property of this is this. So you don't need to take the inverse. You have to take the transpose. Yes.
We're also negating the imaginary part.
Imaginary, and this is for real. Imaginary is coming. The same thing in 2D. If you remember, 2D what we did, we said that the Fourier transform, what was the notation? F, right? So F will be equal to the, or F. So F equals to, or what was that? W, F and W transpose S. So no, this was the word, right? And this is again, I'm talking about the real. When we talk about the complex, then only we have to change into the complex conjugators. Yeah, so here also I can write in this fashion, but A here is not necessarily W or the Fourier transform. It can be any matrix. And any matrix means that you can have any transformation. Yes. This is what I'm saying, that's constant. Now here the book did not use it, but it should be there because it's generalizing it. So that under root 2 is for, sorry, under root n is for the Fourier transform. So when we have the Fourier transform here, then we have to write it, of course. Fine. And this is again just a simple example. Let's say I give you, and here you see this, your question, m or n, they are different size. And even here it's a different sizes. Example. So what I do, although in this example they did not mention what is A2, A3, but they just put it there. So this is actually, don't confuse yourself. This is A2, which means 2 by 2 matrix, and then you have A3 here and transpose, and this is F1. So if I give you this, you can just multiply to find out the transformation. Now these two things defines the transformation. Here it was W, but I can have something. Okay.
So they apply the this.
Yeah, but just assume that this is like this. Don't confuse yourself with 1 by root 2 or this thing. It doesn't matter. Even if you don't write it, it's still okay. But what about the complex? If the A matrix is a complex number, then you just, instead of the just taking the transformation, you have to take the conjugate transformation. But we still have this property that this A complex, sorry, A conjugate transpose is equal to A. So we have this property as well. It's another property of the A matrix. And I think it's easy to follow this one. Right? And I have the A matrix here, and you can play with it to find out. A complex, this is equal to A. So if you do this, you will get this. Yes or no? And A inverse is what? A inverse is A, yeah, Hermitian. Fine. Let's find this. This is now general transformation. Now we can, if we have a discrete Fourier transform, I can have these two equations, right? And this is our R U X, right? And this is X S U X. Yeah, fine. So now I'm just going a bit deep into this, what it will look like, R U X and S U S. What S U X, what it will look like. And based on that, I can have my own transformation, or I can go move towards the transformation. So this is for Fourier, this was the transformation. Now we get 1 by root 2. Now if I plot it for different values of X and U, this is what I get, which makes sense because we have all the frequency components. If you see, the frequencies are actually, we have two because of real and imaginary, and these frequencies are increasing. So what Fourier transform is giving you, it has all the sinusoids, and it is basically breaking down your signal into these sinusoids. So how it will look like? Where is the signal? If I want to transform, where the signal will come up? This is this. So where will be the signal? Your signal will come here, right? Yes or no? So I will just know from this why this happened, because of the summation. I'm summing with this one, right? So I'm just plotting this thing, and then this one, yeah, even this one, not this one, this. But here I just took the numbers. There I'm just plotting this thing. These things just to make sense what is happening. A along, yes, yes. Now see, now I'm just going into deep. Let's say you have. Let me remove this one. And if I have this signal, and what I'm doing, I'm just multiplying this with this with this with this. What I can expect from the output?
It's going to be like whatever 7 by 1.
So it will be, I think it may be related, which frequency is closely matched. I think this is closely matched with this one, right? So ideally, if I just do this, the output, at the output here, I should get 0, 0. There will be some value here, third one, and then 0, 0, 0. This is what I'm giving you the insight that what Fourier transform is doing. So I'm just, now this is just for a simple signal. But if it is a complex signal with so many things, then you can have a simple different portion of these signals. And that's why, because what I did, I spread my signal into the different signals, so that's why we call this as a basis vectors or basis matrix. See what Fourier transform is doing? I think it should be very clear. And now based on that, what I do, I actually in the Fourier transform, because this is a discrete version, I have different sinusoid, right? Real and imaginary. So based on that, I can have other transformation. I can have DCT. What is DCT? In the discrete Fourier transform, I have a complex e power, right? E power is equal to cos plus a sine. So instead of just remove the sign, and we'll discuss what's the benefit of DCT. And I get this thing, so only I get it cos, right? Cos with different frequencies. I'm changing the frequencies, right? See this? So it means I will take my signal or image and I spread into these basis functions. Similarly, we have WHT, which is for the Walsh-Hadamard transformation. They just take just simple square waves with different frequency. Then we have slant transform, which is have the sorted type of waveform. So every person will come up with one transformation. Then we have Haar transform. In Haar transform is actually a first wavelet transform. And here comes the wavelet transform. So wavelet transform, what is happening? We should have a small signal here. So it's like signal which is actually dividing, and it's like a simple instrument. Then we have another one, Batch's wavelet, and then we have pure, and we have STD, which is the yes, we have many. Even if you just see this one, we have so many, and even if you see this, we have so many.
So when they say wavelet transform, what do they mean? Say one common one.
This is what it means. Take this one, multiply with signal, and get the transformation. This is what transformation is. Yeah. And I have some other examples as well. Now, see, this is our Fourier transformation, right? So Fourier transformation will look like this in the 1D case. This is W, right? In 2D case, if I plot this thing, I will get this. If I plot this, I get this. I real and measure. Fine. So now this is like in the signal domain. I'm just spreading my signal into this. However, here I'm just, this is also frequencies, but in 2D. You see, this is just constant one. This is another frequency. So I can say that this is the basis. This is the basis images for any type of images that I have. Basis images. Now, is this clear or not? What?
Usually you multiply with the matrix, and this matrix multiply with the matrix.
Yes.
Now, matrix by, I don't know, it's like this.
So we have two matrices, SU and SV. Transpose, I will get this thing. Or you just plot this thing. This is
Oh, okay, this one.
Yeah. So here what we have, this thing, I'm just plotting this thing, this function, just plot. That's it, in 2D. This thing here. The thing.
How many did this one? Because X, Y, U, V. It's like
X, Y, U, V. So you just take, this is one, and this is another one, and then inside, let's say this is U, this is V, this is Y, and this is X. So you take fix U and V first, and then fix X and take Y. Put it the value, you'll get this thing. Similarly, now the problem here is, you see, there's issue with the Fourier transform. If you see this signal and this signal, it's same, right?
yes, sir.
This and this is same. This and this is same, right? So what we have some sort of redundancy in the Fourier transform, right? This is one point. The other point, if you remember, I take the Fourier transform, I get this thing, repetition, right? Because of the periodicity. And because of the periodicity, I get these. You see, there is some sharp transitions among them. In 1D, it will look like this. So there's some sharp transition whenever there is repetition. So because of this, because you have a sharp transition, it will result in a high frequency component in the Fourier transform. So because of two short terms, one is this sharp transition, the other is redundancy. I move towards the discrete cosine transform, and I get the formula. This is the cos function. So this is DFT, and you see here it's repetition. The signals are the basis function of repetition. There's some redundancy. But however, when it comes to DCT, that there's no redundancy here, no repetition. Plus, if I plot the DCT the discontinuities is very smooth. So because of that, the DCT is more preferable in image processing as compared to DFT. This just shows the basis of DFT and the DCT. And so if I just plot this is smoothness, because the images are not placed like this. This image is the same image, so because of the same image placed, there's some discontinuity here. But here, if you see, because of the structure of DCT, this is the image and this is the invert of it. So it's like, yeah, it's actually each other. So image and the other image start from there, the other is that. So anyhow, we don't need to go into details, because DCT, if you start doing it, it's like too much. You remember DFT was something like this. But so what was happening? Let's say you have sinusoidal. It should look like this. So again, this comes as a redundancy. You have one pulse, while you have another one, right? But in DCT, no. DCT, and before, this is after FT, this is after shifting. Remember that? If you don't have shift, the low frequencies was here, right? Yes. So that's why we shifted it, just to make sure that our filter is good enough, and we discussed this why we do it. But in DCT, the good thing is only low frequencies are here, and if I'm going like this thing, these are the high frequencies. So this is a good thing. We don't have any redundancy, complexity is less. So main thing here is what the transformation, how we do the transformation, plus why DFT is not good and why you are using DCT. So this is our main thing. We don't need to go much detail. And again, this is a DCT matrix, nothing else. Similarly, we can have sine as well. It's well, of course, but the use of sine is not that much. So therefore, we will not discuss it. Just
providing a good definition and result in image side.
Okay.
The sine is not providing.
Yes, it's not providing, but that's why it's not being used. Okay. Fine. So this is just again the sine transformation with the basis vectors and basis images, and this is just the same thing with the numbers. Just to give you a creative that what will be the A matrix. The A matrix you have, what will be look like? Yes.
What's giving different results from
because there was some reason. One is the compactness. Cos provides more compactness in the Fourier transform, and that's why the cos also we use it for decompression. Why? Because it is like compact, let's say like this, so I can ignore some part of it. It does not have the information of the image. So it means that I'm reducing the size of the image.
You mean for DCT or
DCT. So what was the Haar transform? It is again a square. However, what is happening is I am reducing the size. So when in the technical terminology, I say scales. And what I'm doing, first time you see the first one is like this. The second one is this thing, and then we have this, and then the same thing shifted, right? then again, because nothing else I can do. So again, I reduce the size.
And shift
Okay.
it with the same.
And then shift unless I go here. Again, reduce the size. So what I'm doing, I'm scaling plus shifting, which we call it translation. And this is what wavelets are. Only your favorite wavelets. Nothing else. Change the shape. Now here I'm doing square. Change the shape. Let's say I can have, let's say, like this one, and then I can have, let's me show you. So yeah.
One of the papers, he was talking about like detection of like resonance. So he was comparing wavelet in 3D and STFT in 2D.
This is what, you know, if STFT, if I apply images, how much, what I get. So wavelet apply 3D, all images get 3D.
Because and maybe I need to read it again. Did he take 1D signal?
Yeah,
he
if you
used,
take 1D, definitely it becomes 2D.
yeah.
For
So maybe he used STFT for 2D and he went further to wavelet in 3D.
Or sometimes if he wants 1D to 3D, it might be, he might be dividing the signal first. Divide the signal, and on that dividing apply the wavelet. So it means that you become 3D. Let's say you have a signal, I divide by 2, I get 2 signals. Now in these 2 signals, here I apply wavelet, become 2D, become 2D.
I cut it into half here, like first 5 seconds.
Yes.
And the last 5 seconds.
Yes. Maybe this is more. Maybe you can. Yeah. So the wavelets are also clear for you. Now changing this thing will change the wavelet. So that DB4, which was patches and pure, they just propose different wavelet. Like instead of here the wavelet is, this is the wavelet that I'm changing. I'm scaling and translation. Yes or no? Scaling, reducing it, and then translation. That's it. So let's say instead of this, I define any other thing. Let's say this, which is called a Richter wavelet. Okay, or I just define another like this one, which is called minimum phase wavelet. Then we have modelet wavelet. So any wavelet to just and do the same process, and then multiply with the signal, you get a wavelet. And similarly, if I just draw this one in the image domain, I will get this. See, this is all ones, right? So this is 1. Yes. Then this is 1 and minus 1. So now here I can either do 1 minus 1 like this, or I can do 1 minus 1 like this. Now I have 2 degrees of freedom. Yes or no? Similarly, if I divide again by 2, so I get this thing. 1, this is 1 and this is 0. But again, this can be like this, this can be like this, can be like this. Yes or no? So I'm dividing the wavelet because I'm trying to fill all the gaps like scaling and translation in 1D plane and in 2D plane. And then I'm just taking the image and applying it on the image. Yes or no? Have you heard about, for the wavelet, we have 2 terms. One is very common, one is not common. One is called mother wavelet. What is mother wavelet? This is mother wavelet because all of them, they are derived from it. It's a child of them. We call this like scaling down, right? Yes or no? That's why it's called the mother wavelet. Here the mother wavelet is this, and then I divide it based on the scale. And the first one will always be like this. So this is called the father wavelet. Sometimes called father wavelet, it is not common used. Is this clear? So a simple example, and this is the last slide. If I want to apply this Haar transform onto an image, so how I can do it? Let's say I have only these ones. Let's see, I have these four, right? So if I apply on this image, this is 1, 1, 1, which was the first one, right? 1, 1, 1. The second one is 1, 1, minus 1. The third one is 1, 1, minus 1. The fourth is 1, 1, and minus 1, minus 1. Yes or no? So if I apply, I take the image, I apply for this one, multiply, slide, and this one, so I get these 4. Multiplying this will get this and this. So it's very, why you are getting here the actual picture and others not? Maybe this is a good question for you.
Special question for Hassan. He will answer it.
Yes.
Again, repeat the question.
I get the same image of this picture here, but here I don't get it.
Because 1.1 is nuance of the image, and on the first.
This is what, if you go inside the wavelet, this is what it's get. This is what smoothing filter. So I get this same figure. Here what I'm doing, sharpening. This is again sharpening, but this is like in this direction, this is like in this direction, and this is like in diagonal direction. So in other words, wavelet is everything that we studied in one thing, one step. So that's why it's much more sense. I think for that, I think we are done. I think for today's lecture, you have to make sure that you know how general transform can be presented. You should know what is STFT, and then definitely from that you should have a knowledge of DCT, that what it is and what is not, and then the Haar transform, how it will look like, or in general the wavelets. So I think if it is clear to you, I think we covered all of the basics of it. Now it's up to you if you want to apply or not to apply. Just to get this.
So again, Haar is one of the wavelets. There's many.
So many.
So what is wavelet again?
Wavelet is just wave, small wave that is present for a small duration. So in wavelet, as I mentioned, I can define a mother wavelet, like this is the mother wavelet. The others are derived from this one. And the first one, which is always 1, 1, 1, we can call it as a father wavelet.
The first one is to be said, right? But the second.
Yes.
So DCT is not wavelets. DCT is just a type of
Yeah, it's like a DFT with a sign 0. So although I give you a lot of information, but the function is still very basic. And I just give DFT with sign 0. And the wavelet is again a type of transformation. Instead of sign, you have wavelet. This is what the information is. Okay, if you understand this, you have done all the transformations. You can have your own transformation.